Welcome to CSAI Think Tinker Learn. Today, we are moving into the transport layer for the Senior Engineer's Guide to TLS and mTLS fundamentals. Before we tear this engine apart, please hit that like button, share this video, and subscribe to support the channel. This is a part of my new high-level system design series, designed to give you the architecture big picture quickly. For deep dive articles and diagrams, please mention that in the comments. I'll make sure I make those videos specifically on a particular topic within these high-level topics. In addition to this, I have created a GitHub pages which are available at this CSTTL GitHub IO System Design IO. The site is a work in progress, but anything that you see in hyperlink, those are the completed articles. So this will continue as I continue forward. Today we are putting a high-level overview on TLS and mTLS fundamental. This is a pretty detailed article that you can find here. In addition, if you want me to make any video, as I mentioned earlier, please do put in the comments, and I'll make sure that you have the article or the deep dive available. Okay, now let's look at how we can secure the wires. Okay, now TLS is a game of two gears. Asymmetric math like RSA or ECDHE solves a key distribution problem: how to share a secret over a hostile network without anyone eavesdropping. However, asymmetric math is computationally very expensive. Symmetric math like AES is incredibly fast but requires both sides to already have the secret. TLS uses the big gear, which is the asymmetric part, once to safely hand off a session key, then switches entirely to small gears, which is the symmetric, for the actual data transfer. A critical warning here: if you're using plain RSA for key exchange, you lose forward secrecy. If an attacker steals your server's private key tomorrow, they can retroactively decrypt every packet that they intercepted yesterday. Always use ECDHE for ephemeral keys to ensure today's secret say secret tomorrow. Encryption is useless if you are talking to the wrong person. That's where X509 certificates come in. A certificate mathematically binds a public key to an identity using a digital signature. Your OS and browser trust a set of root certificate authorities. When you visit a site, your browser walks the chain of trust upwards from the leaf cert to the intermediate and finally to the root. If the chain is broken, the connection is considered untrusted. One major gotcha in production is modern clients completely ignore the common name or CN field. If your certificate lacks a subject alternative name or SAN extension which matches the host, the handshake will fail immediately. Always check your SANs. The TLS handshake is evolved from a slow walk to a sprint now. Legacy TLS required multiple round trips before data could be sent. TLS 1.3 stripped away decades of bloated, insecure crypto and merged the key exchange into the very first client hello message. This reduced the handshake to a single round trip. Under the hood, the client and server negotiate cipher suites, a contract of algorithms for key exchange, authentication, and encryption. A word of caution: if your load balancers still support SSL3 or TLS1, you are vulnerable to legacy attacks like Footer. Rip them out immediately. In modern production, TLS 1.2 is the floor and 1.3 is the goal. In standard TLS, the server proves its identity to the client, but the client remains anonymous at the transport layer. We usually handle client identity at the application layer using API keys or passwords. But here's the problem: API keys are bearer tokens. Whoever holds a string gets access. They have no inherent cryptographic identity. If an attacker lifts an API key from your internal logs or GitHub repo, they can impersonate a microservice indefinitely. The server is completely blind to who is actually sending the token through the encrypted tunnel. Mutual TLS or mTLS turns security into a two-way street. In this zero trust model, the server challenges the client to prove its identity before the handshake even completes. The server sends a certificate request. The client must present its X509 certificate. This is a gold standard for service to service communication. But beware of the half open trap. If you set your server to SSL verify client as optional, considered of required. The server will still accept connection without certificates. This neutralizes your security guarantee while giving you a false sense of protection. In MTLS, it's all or nothing. Sending a public certificate isn't enough proof of identity. After all, public certificates are public. To prove ownership, the client must demonstrate it possesses a corresponding private key. It does this by signing a hash of the entire handshake transcript. This handshake transcript is a unique fingerprint of the current conversation. Since only the true owner of the private key can generate that signature, a server can verify the identity with certainty. The dependency here is a physical security. If your private key file permissions are too loose on the host machine, your entire cryptographic identity is compromised. Guard your .key files with um, like they are your crown jewels. Managing certificates for thousands of microservices manually is a nightmare. This is why we use service meshes like Istio or Linkerd. A sidecar proxy, usually Envoy, sits next to the application container. It intercepts plain text traffic and upgrades to mTLS transparently. It uses framework like Spife and Spire to automatically rotate short-lived certificates, sometimes every 24 hours. A warning for developers. Don't try to be clever in your code. If your application attempts to do its own TLS termination instead of trusting the local sidecar proxy, you'll create routing loops and drop packets. Let the mesh handle the plumbing. The old castle and moat topology, where you have had a hard outer shell and a soft, trusted interior, is dead. In a modern architecture, we assume the internet network is already compromised. Zero trust mandates, trust nothing, verify everything. In this model, identity is cryptographic, not IP based. Just because a request comes from an internal 10xxx IP address doesn't mean it's safe. Every single hop between microservices must be re-authenticated and encrypted. This prevents lateral movement where an attacker breaches the one low-level security and uses it to sniff traffic across the entire data center. What happens when the key is compromised? We need a way to kill it immediately. Certificates naturally expire, but for emergency kills, we use revocation. CRLs are downloaded blockless, but they can get massive and stale. OCSP is a real-time query to the CA, but it adds latency. The modern solution is OCSP stapling, where the server periodically gets a proof of validity from the certificate authority and staples it to the certificate during the handshake. This saves a client a network hop. If your service fails to check these revocation pathways, it will gleefully accept a compromised, revoked certificate long after the attack has taken control. When choosing an identity strategy, don't view these as competitors. View them as layers. API keys are great for simple third-party integration. JWTs are perfect for stateless user-to-service auth because they carry user context. OAuth2 is the standard for delegated access, but MTLS is the heavyweight champion for machine-to-machine security. The ultimate enterprise pattern is layered. Use MTLS to prove which machine is talking to the transport layer and a JWT inside that tunnel to prove which user initiated the request at the application layer. We have covered the math and the production reality. To recap the traps, avoid certificate pinning as it breaks automated rotation. Always use SAN fields over CN and never settle for plain RSA if you want forward secrecy. Okay. Now I have a question for the community. If your current stack, are you still relying on castle and moat perimeter, or have you fully migrated to zero trust MTLS architecture? Tell us about your migration challenges in the comments. If this dive helped you understand the engine better, please like, share, and subscribe to CSAI Think Tinker Learn. Check out the full series at our site. Link will be in the description. Thanks for watching and stay secure.